Okay, this is the second hour of Physics 1A for June 2nd, and we're now going to continue talking about simple harmonic motion in particular, this box on a spring system here that we're talking about. So we're going to solve this problem, but I guess I realized that it's probably worthwhile to look back at what we were talking about and discuss the meaning of why is the angular frequency related to spring constant divided by mass, and what does this mean that x of t is equal to a cosine omega t plus phi? Let's talk about that briefly. All right, so we already accomplished what we were trying to accomplish there. So this is our system, right? And our box basically oscillates back and forth and back and forth and back and forth. And this is the type of motion that it undergoes. So the first thing I would say is we said that we could represent what the box was doing with this function, right? And again, understand that this is a general equation where the phi is going to be something that we're going to manipulate it depending on certain situations. In this case, our object starts off at x equal to a, right? So let's see if we can actually figure out what this phi thing represents right here, okay? So if I know that we release it from rest, and this is our initial position, and I say that this happens at t equal to 0 right here, right? Then that means that if I put x of 0 here, that this should be equal to what? What should the x-coordinate of our system be at t equal to 0? A, right? Yeah. Should be equal to a, right? So if I plug that into my equation, then I'm going to have a cosine of 0 plus phi, because t is 0, or just a cos phi. So what should phi be equal to then? Yeah, 0. It could also be 2 pi, right? Or it could be 4 pi, or it could be any of these things. But it's basically equal to 0, or 2 pi, or 4 pi. Wait, is cosine of pi? That would also work, right? No, because cosine of pi would be -1, right? So it has to be 0, 2 pi, 4 pi, etc., right? And of course, we'll always keep these things simple and just choose the simplest answer. So phi equal to 0, that seems reasonable. Okay, well that means that our actual function for this equation is just x of t is equal to a cos of omega t. And what does that look like? Well, if I were to plot that function, where I plot x on the normal axis that we would call y, and t here, then it's basically going to look like this, right? It's going to, at t equal to 0, it's going to be right here, at the point that we call a. When we get to a t that's about half a period later, it's going to be at -a, and eventually it's going to get back around to here. And we can even say at what time each of these occur. If we say that t represents the period of the motion, where t is equal to it's 2 pi over omega, right? So t is the period, and it's equal to 2 pi divided by the angular frequency. Then we can say, if this is t equal to 0, then at what point is this, and this, and this, and this? So this is, the first one's going to be at t equal to 1/4 the period. At what point is it going to be at x equal to -a? What time is that going to occur at? Not 2 pi. It's going to be the period divided by 2. And this time over here is going to be the period, it's going to be 3t over 4. And no, I left something out. I left one out. Oops. Sorry. This point will be 3t over 4. And this point will be t. And then it will repeat itself. So going back to our picture right here then, yeah, this was t equal to 0. This is going to represent t equal to t over 4, 1/4 period. This is going to be t equal to 3/4, half the period. This is going to be t equal to 3/4 of the period. And we come back to here where t is going to be equal to the period, where it repeats itself, right? So that's kind of our picture of what's happening. And one thing that we can also do, and I'll draw a line, but I'm going to get rid of it. Maybe I'll draw it in yellow so it's not too. If I were to draw a line that goes from this to this to this, and then back to here again, it's on its side, but can you see that that also kind of traces out a cosine curve? We just kind of map out where the object is over time. Does that help you to understand why we say that this is what the function is? And that it fits with the, you just take a system like this and you ask, suppose that I were to take the object and I pull it to the right by some distance, can you tell me where it's going to be at any point in time? And the answer is, yeah, you can. It just follows this. Pick any moment in time. I say time starts at 0. I can tell you exactly where the object's going to be 100 seconds later, where it's going to be 1,000 seconds later, and so on and so forth, right? And it's going to follow a cosine curve. So simple harmonic motion is directly tied to sometimes it could be called sinusoidal motion because it follows like a sine wave or a cosine wave. But yeah. And the nice thing about sine functions and cosine functions is they basically repeat themselves forever, right? Just like what this thing is doing, it's repeating its motion over and over and over again. Does this all make sense to everyone? Does anyone have any questions? What about this? What if we take the exact same system, okay, but instead of releasing it from rest at this location here, what if we started from here? What if this represented t equal to 0 right here? How would that have changed what we did here? What would the value of phi be? What would the phase constant be if we started from this, if this was t equal to 0? Does the question make sense? Should I set it up as a new question? I figured you could probably imagine this in your mind. Yep, so here, if this was our initial position, then x of 0 would be what? It would be negative a, right? If this is our initial position, x of 0, the x at time equals 0 would be negative a, right? So then this is what it would look like. It would look like this. We'd write x of 0 would be equal to negative a, which should be equal to a cosine phi. So then what would phi need to be equal to? Pi. Yep. So what does the phase constant do? What's the point of it? What does it do? What does it tell you? I guess is a better way of saying it. What does it tell you? What information is given by this quantity, phi? Yeah, the starting point, exactly. The starting point, right? Another possibility of where we start the object would be we could start from this location here. And since we're at the equilibrium position, we're not going to get motion unless we push it, right? So another possibility would be the object starts in the middle and we give it a velocity to the left, right? And if we do that, that's going to give us a different value for the phase constant, right? So all the phase constant does is, as you says, it tells you something about the initial starting point in the problem, right? Okay. Any questions before we start talking about the meaning of this quantity right here? That's a good question. How is angular velocity omega related to simple harmonic motion of the box when the spring and when the box is not rotating, right? So it's not angular velocity in this case, it's angular frequency. That's a really good question. So this represents the angular frequency. And it just turns out in this case, angular velocity is a vector. Angular frequency is a scalar. That's one thing that's different between them. When you talk about, for example, an object that's rotating, yeah, it's kind of confusing because we use the exact same symbol for both, and I think that's because they have the same units, right? If I have an object that's rotating around like this, then it has an angular frequency that points up. Angular speed, sorry. Angular velocity. So this is angular velocity. And this is angular frequency. The biggest difference that I can think of is that angular velocity obviously describes something that's rotating. Angular frequency can just describe something that is going through periodic motion. So periodic motion, we can always describe, for any type of periodic motion, we can describe period, frequency, and angular frequency. For an object that's rotating, a rotating object kind of has a lot of the same properties, right? Because if you have an object that has a certain angular velocity, you can use, and let's say it's 2 pi radians per second, okay? Let's say your angular velocity is 2 pi radians per second. You can use that to figure out period, right? The period would be 1 second, right? According to this equation. If omega was 2 pi radians per second, then your period is 1 second, right? And you can also figure out the frequency, which would be 1 revolution per second, right? So in both cases, all the same relationships exist between period, omega, and frequency. So I think that's why we use the same symbol. But it's good of you to point out that they're different from each other. Does that make more sense? Okay, yeah, right. And I have to apologize because I'm not super precise with my words. I try to be, but I will probably call this one angular speed at some point by accident. I apologize for that. Now let's look at this quantity right here, because this is the only part of this that we can really harken back to the physics that we've learned this semester, I think. Not the only part, but... So why is this the case? Why does the angular frequency of this motion depend on the spring constant and mass, and why is the spring constant in the numerator? Why is the mass in the denominator? And can we make any sense of this? Okay? So what this is telling us is, let's look at spring constant first, that the angular frequency is going to be larger when the spring constant is larger. Is that reasonable? That's like saying that it's going to oscillate back and forth faster when the spring constant is bigger. Right? That's what that means, right? If you were to quadruple the spring constant, well, if you quadruple the spring constant, what happens to the angular frequency? If you make this 4 times as big, what happens to this one? Twice as big, right? Because you're square rooting it, yeah. So the bigger the spring gets, the faster that it oscillates back and forth, okay? And that's because the bigger that the spring constant is, the bigger that this thing is going to be, right? The restoring force is going to be bigger. So it's going to have a natural force that's going to push it back to equilibrium much more quickly. The acceleration will be greater, and so on and so forth. Okay, that's another way you could say it, is you could look at acceleration. According to this, acceleration is equal to a times omega squared, and that should make sense. That the size of the acceleration is proportional to the spring constant, right? Okay, what about the thing in the denominator, the mass? This says that omega will be larger when the mass is small, and omega will be smaller when the mass is big. Is that reasonable? If I have a big, massive object on here, it is reasonable, right? Yeah. Because if this object is really massive, it has a lot of inertia, which means it's going to be really sluggish when you try to move it back and forth. If you make the mass a lot bigger, like consider a spring and you attach it to a golf ball, and then you take the same spring and you attach it to a bowling ball. The golf ball is going to oscillate back and forth really fast, but the bowling ball is going to oscillate back and forth and back and forth really slowly. So the golf ball will do this, but the bowling ball goes really slowly. Just like if you were to pick up a bowling ball, right, or a very heavy object, right, and you try to move it side to side, you're going to notice very quickly that it's hard to take a bowling ball and just swing it back and forth like this, right? I could even use my jug of water as an example. It's not that heavy, but if I take this jug of water and I try to move it back and forth, right when I get to the ends and I try to move it around, I feel it. Like it's moving this way, and I feel that it wants to keep going that way, and I have to try really hard to keep it from continuing in that motion, right? But whereas if I pick up like this stylus and move it back and forth, I'm not going to feel any resistance at all because the stylus weighs less than my hand does, and so that's not hard for me to move it back and forth, right? So it's the same concept here, where the spring is like my arm and the box is like the thing that I'm holding. Okay, so that should make some kind of sense. So if we have a good understanding of like the physics of what's happening and the mathematics that describe it, let's see if we can't solve some of these problems and go from there. And hopefully we'll have enough time to also talk about pendulums. We should. Okay, so here's our problem. It says we're given something that's moving with simple harmonic motion, and we're told that the coordinate x as a function of time is given by this expression. It's 4. I'm going to put a unit on here. Oh no, it says x is in meters. Yeah, so x is in meters. I was going to make this in meters, but because 4 meters is just really big, but that's okay. Cosine of pi times t plus pi over 4. And I'm actually going to come in here and put some units in just because it bothers me when I don't see units. So this is going to be pi over 4 radians for the phase constant. And for this one will be radians per second. I'll put some parentheses around that too. So that's our function. And this problem is really quite simple. So let's go through it. And the next one will be a little harder, and then after that it'll get a little harder than that. So the first part A, says find A, omega, and t. Okay? And you will have problems like this on your homework too. It is very easy. What's A? Well, let's look at our general expression. It's 4, that's right. Our general expression was that x of t was equal to A cos omega t, right? Oh, whoops, plus phi. So A just shows up right there. It's just 4. Okay, what's omega equal to? Well, omega is the thing that's multiplied by t. It's that, so it's just pi, yeah. And what's the period? Well, for that, we need an equation, and period is related to angular frequency as 2 pi divided by omega. So 2 pi divided by pi is going to be 2, and the units for that are seconds. Kind of look like 25, so 2 seconds. All right, part B. We want to calculate Vmax and Amax. From above, we said that the maximum velocity is given by taking the size of the amplitude and multiplying by the angular speed. So that's going to be 4 meters multiplied by pi radians per second. So we're going to give out something like 12 meters per second. Let's see what we actually get then. So this is about 12.6 meters per second. And again, you don't have to write the radians here. All right. Next is Amax. Amax is given by just taking A times omega squared. Super easy. You just do 4 meters and we multiply by pi radians per second whole squared, and that gives us about 39.5. That seems like a really big number. Meters per second squared. Huge acceleration. About 4 times the acceleration of gravity. All right. Oh, sorry, that's part C. I skipped part B, my bad. Well, the good thing is that part C is actually good to do before part B, because then we don't have to do the calculations. Part B, we were supposed to find v of t. Well, v of t is just going to be the derivative of this one. And the derivative of this would be negative 4 meters multiplied by the derivative of cosine, which is negative sine, pi t plus pi over 4. I don't want to write the units again. I think it will just confuse you. Multiplied by the derivative of the inside, which is pi, which we already saw that 4 times pi was equal to 12.6, so this becomes negative 12.6 meters per second times the sine of pi times t plus pi over 4. So that's v of t. It was cosine, right? So cosine of the derivative is negative sine. And then the acceleration is a function of time. I'm just going to go ahead and put so basically it's going to be this times pi, which we saw was 39.5. And we take the derivative of sine, which is cosine. The negative sign will still be out in front. So we'll have negative 39.5 meters per second squared, cosine of pi t plus pi over 4. Okay. All right. Is everyone good on parts A, B, and C? Let me know if there are any questions. Okay, part D. The phase angle at 2 seconds. This is kind of a trick question because the phase angle doesn't change. The phase angle is just this thing. So phi is equal to pi over 4. And then for part E, we want to find delta x of the body between t equal to 0 and t equal to 1 seconds. How can we do that?
Wouldn't we be able to plug in for 1 and 0 and then subtract the 2?
So yeah, something like x at 1 seconds minus x at 0 seconds, right?
Yeah.
Okay. Why don't you all calculate this? Remember that you need to have your calculator in radians now. Why don't you all calculate that? X at 1 minus x at 0. Okay, what do y'all get? I probably made a mistake though. Question mark, you got 0? I didn't get 0. Is your calculator in radians or degrees? Did I make a mistake? Let's see. No. You guys all agree it's okay. You made a mistake. Okay, cool. It's negative 5.66. That's what I got to. Yeah, 5.66.
Professor, I'm so confused about the calculations because I have it in radian mode still.
Well, you now know what the right answer is. You can see the value of what x of 1 is and x of 0 is, so try it again until you get the right answer. Okay? Does that work, Chase?
Yeah, but I'm just confused on like how you got those numbers because I have the thing in radian mode.
So x of 1 seconds, just to write out what it would be 4 meters times the cosine of pi multiplied by 1 second plus pi over 4. You plug all that into your calculator and you do it without making any mistakes. Ugh, why must it do this with 4s? Why must it do this? Pi over 4. I did it multiple times and I kept getting this answer of negative 2.83. So just be careful about the way that you're putting it in, I guess. I think it's an input error, most likely. It's something about the way you put it in. But you'll figure it out. I'm confident you can do it. All right, so there we go. Yeah, honestly, I didn't write this problem, and I don't really understand what this means. I think there's two possibilities of what it means. Either it just means find the phase angle, which obviously it never changes. Or the other thing that it could mean is without this word to find the phase at t equal to 2 seconds, the phase would be this entire quantity right here. So it would be like 2 pi plus pi over 4, which would be like 7 pi over 4. But you're not going to see these this particular type of question show up on homework problems, so I don't think you need to worry about it. It's just the teacher that wrote this particular problem, I guess, yeah. Yeah, phase is this quantity, I think, and phase angle is this quantity here, yeah. But don't worry too much about it. It is just a bad, it's a confusingly, that portion of the problem is confusingly written, especially with the typo. I don't know what the typo is supposed to represent. Okay, so we did this one. We definitely want to do at least these two, and hopefully this before the end of the day. We should easily be able to do that. That shouldn't be a problem. But we have to derive the information about simple pendulums and physical pendulums too, so that's going to take some time. Alrighty, so now we try one that gets... before we do this, before I forget, because I will forget, let's talk about energy in simple harmonic motion. This is not too complicated. Okay, so we've learned in this semester that there's this thing that's called mechanical energy. We use the symbol E for that, and it's equal to the kinetic energy of a system plus the potential energy of a system. Now, in this particular case, the mechanical energy for the spring plus mass system is going to be its kinetic energy, which at any moment in time will be given by 1/2 mv squared, plus its potential energy, which is going to be given by 1/2 k times x squared, right? This is going to represent the total energy of our system. So I'm going to call this E total, right? Now, the values of v and x in the case of simple harmonic motion take on multiple values, right? X can vary between negative a and positive a. The velocity can vary between negative Vmax and positive Vmax, okay? And as the object undergoes its motion, it kind of goes through an exchange of energy, okay? In fact, we can come back to our original picture of the motion right here and we can start to talk about that. When the system is in its equilibrium position and not moving, there is no energy, okay? The moment that we pull the system to here and we get to a position where we're at x equal to a, which is x max, I would say at this point that the potential energy is maximum. Because the potential energy at this point is going to be equal to 1/2 k times the x squared, which is a squared. That's what the potential energy is at this point. when the object crosses through the middle, it's going to have a potential energy that's equal to 0, but its kinetic energy is going to be 1/2 mv max squared. And then when it gets to here, the kinetic energy is going to be 0, but the potential energy is going to be at maximum. And back to here, we're at, this is K is max, and the potential energy is 0. So there's this exchange of energy that's happening throughout the process. But at any moment in time, if you know the velocity and you know the position, you can describe the total energy, right? Now, the other thing we can do is we can say that the maximum quantity you can have for the potential energy would occur when x is equal to the amplitude, right? This is the maximum value you can get for the potential energy, right? And at this time, v is equal to 0, right? When the potential energy is maximum, then the velocity is 0, right? So we could also say that this same quantity represents the total energy of the system. So the total energy of the system, we could write it like this, 1/2 k times the amplitude squared. Or we could write it as 1/2 m times v max squared. But we know what v max is. V max is equal to a times omega. And if we plug that in here, you'll see that we get the same thing. If I plug in for v max a times omega, then I'm going to get a squared omega squared, which is 1/2 m times omega squared. But what's omega equal to? Well, omega squared was equal to k over m. So whether we use v max or whether we use x max, it doesn't matter. The total energy is always given by just 1/2 ka squared. That means that we can write down this expression. 1/2 ka squared represents the total energy of our system. At any moment in time, it doesn't matter where the object is, the total energy will always be the same because the system is frictionless and there's no energy loss. So we get this general expression right here that's really just an energy relationship. And we can cancel 1/2 out of every term. So we can write this as ka squared is equal to, what would be left? mv squared plus kx squared. The next thing that we can do is we can divide through by m. So we get k over m, a squared. I'm going to subtract this term over to here. So basically all I did here was I multiplied this entire thing by 1 over m, and then I manipulated it by moving the x squared term to the left-hand side. But look, we have k over m that showed up again. So k over m was equal to omega squared. So now we can write omega squared times a squared minus x squared is equal to v. And then we can square root both sides. And we get this nice general relationship, which is plus or minus omega multiplied by the square root of a squared minus x squared is equal to the velocity. This is probably a relationship that's going to be pretty helpful to you at some point when you're doing your homework, because what this tells us is what the velocity is, not as a function of time, but as a function of the x-coordinate, right? Because a and omega are both constants, so this gives us the velocity if you give it a value for x. And you can check it. What do you get if you put x equal to a? You get 0. Is that right? Let's go back and look at our picture again. That implies that whenever x is equal to... Sorry, what did I say? You put x equal to a. When x is equal to a, that implies the velocity is 0. And that is what we had before. Right here, when x was equal to a, the velocity was 0. And down here, when x is equal to negative a, the velocity was also equal to 0, because negative a would also work because in our equation, x is squared, right? So this is kind of a summary of the information that you can garner from energy for simple harmonic motion, but it's important to understand, this is something I'm going to talk about at the end of class today, that you don't need to memorize this equation, right? You just need to memorize that equation. And this is an equation you probably already memorized, right? That energy is just kinetic energy plus potential energy. And then you need to remember potential energy for a spring is 1/2 kx squared. So there's little details you have to remember, but you can use this equation, but it's really just a special result of the more general idea, which is that energy is conserved in this process. Okay? All right. I want to say one other thing here too. Is it obvious from this one? How else can we write this? We could also write this as a squared is equal to v squared over omega squared plus x squared. That's not so obvious. Okay, I'm not going to bother with it right now. I don't want to get confusing by trying to figure out how this is going to work. All right, so that's energy for simple harmonic motion. Let's go on to these next two problems that we want to solve. Energy is conserved in simple harmonic motion problems. That is the main thing to take away from what we just talked about. And for some reason, I think I deleted... Wait, let's see. Maybe if I paste it again. Oh, it's still there. Good. Okay. Here's the problem. Again, this one's going to be pretty simple. A particle attached to a spring undergoes simple harmonic motion. The maximum acceleration of the particle is 18 meters per second squared. The maximum speed is 3 meters per second. And we want to find the frequency, omega, or f, and the amplitude. Any ideas? How can we do that? Use the energy equation. Let's see. The energy equation right here tells us something about amplitude, x, and v. Yeah, I think we need to do what Joanne just said. We know that A max is also equal to a times omega squared. That was one of the things that we figured out when we derived all of these here. Oh, here. That A max is equal to this. And V max is equal to this. Right? We know what A is and we know what V is. So if we write, for example, A max divided by V max, there's other ways you could do this. This is just one way to do it. This would be equal to A omega squared divided by A times omega, which is to say it's equal to just omega, right? And we know what A max is. It's 18. And we know what V max is. It's 3. That means that omega is 6. If I did the math right. So we get omega, and then we can use either equation, probably this one's the easiest, to find what A is. So this is part A. Part B. Part B, we would take, yeah, we know what Vmax is. So if we take Vmax and we divide by omega, that should give us A, according to that equation. So Vmax was equal to 3, and omega is 6. So A would be 0.5 meters, or 50 centimeters. All right, that's kind of a little bit... I said it was an easy problem, but I think it's actually kind of tricky because it's not super obvious just because you're given this and you're given this, how you're going to go about finding these things. But that's how you would do it. Any questions? Yeah, simple once you know what you need to do. I'm sure you all could have figured that out if I gave you enough time. You'd figure it out on your own. You'd look back at your notes and you figure it out. Okay, one more. One more box on a spring, and then we'll talk about the pendulum. What time we got? 3:51. I think we can solve this problem in roughly 9 minutes, I think. A particle undergoes simple harmonic motion with angular frequency of 4 radians per second. Just write down the information as we get it. So omega is 4. Initially, the particle is 6 millimeters to the right of its equilibrium position, and it's moving to the right with the speed of 3.2 centimeters per second. Where will the particle be 0.4 seconds later? I like this problem because it doesn't just tell you what you need to do. It doesn't even break down the steps. And there are multiple steps. So this requires that you're really comfortable with this stuff. It's pretty tricky. So, what information do we know? Well, it's obvious. It says that we have simple harmonic motion. The angular frequency is 4 radians per second. Notice in this case, it doesn't say anything about a box and a spring, right? It just says a particle undergoes simple harmonic motion, okay? And that's because this concept also I thought there was someone on my door. This concept of simple harmonic motion doesn't just apply to this system. It applies to all kinds of systems. And all those systems have very similar features where they have a function for position that's given by something like this. There is an angular frequency. Now, what that angular frequency is will depend on the system, okay? Will depend on the system. But this topic of what we're discussing, it doesn't just refer to boxes and springs. It refers to all types of objects that oscillate. And one thing that you're going to learn if you keep going through physics, if you take physics 1b and you take physics 1d, is that all particles, atoms, electrons, particles, right? The smallest things that things are made out of that you learn about. They all have this natural frequency that they oscillate at. And when they're put in certain systems, they might, oscillate in a different way. When you heat up their temperature, they oscillate even more. So part of the reason why simple harmonic motion is something that we study in physics 1a, which is, the basics of physics before you go on to more complicated things, is because this concept is going to show up over and over and over again in your study of physics. From classical physics in the study of the motion of particles when they have a hot temperature versus a cold temperature, to describing the way that particles emit energy and photons when you get to physics 1d. And it's also going to refer to the motion of electrons in circuits in physics 1c. Simple harmonic motion is as much a part of nature as projectile motion is, right? Projectile motion is when you throw an object. Simple harmonic motion is what happens when an object vibrates. And like I said, all things vibrate. So in this problem, it doesn't say anything about a box and a spring. It says a particle. Okay, so particle undergoes simple harmonic motion. We know the angular speed. And we also know that initially the particle is 6 millimeters to the right of its equilibrium position. And it's moving to the right with a speed of 3.2 centimeters per second. So we can kind of draw that. Let's just put a little line right here. And let's say that our equilibrium position is right here. So that's x equal to 0. That's equilibrium. It says initially the particle is 6 millimeters to the right of its equilibrium position. So let's say that this is 6 millimeters right here. So this is going to be x equal to, and it says 6 millimeters to the right, so that's why I'm putting it on the right side. So I think it's okay to call this positive 6 millimeters, right? And what else does it tell us? It says it's moving to the right, so it has a velocity at this location. Maybe we use a different color so it comes up a little better. Its velocity is going to the right, and its velocity at this moment in time is equal to 3.2 centimeters per second, right? So that's all the information we really have, right? This particle, it's oscillating on this type of system, and initially, these are the values that we have, okay? Where will the particle be 0.4 seconds later? Well, answering that question is going to be very difficult before we know more about the motion of this object, before we know, really, what the equation of motion is for this object. That is to say, this thing. Right? If we knew this right here, and it says initially, right? So what's the time for this point right here? What's t equal to right here? 0. Yep. So this system is not like the system we were talking about before, in the sense that before we said that we pulled the box to the right and we just let it go, right? We just let it go and it oscillated. So it had an initial velocity of 0, and its initial position was just a, right? So we're somewhere in between here, right? All right. So what do these pieces of information represent then? What is x equal to 6 millimeters? If I was to write that down as kind of like a given here, how could I write it down? It's a distance, yeah. How could I write it down? And maybe think about it in terms of this equation right here. It's the initial position. How can I write that down? Okay, I'm just gonna say it because I don't want to. It isn't the amplitude, because the amplitude only occurs when velocity is 0, right? Let's look back at our energy equation. X is equal to a, in this equation, x is equal to a only when x is equal to a only when v is 0, right? So this is not the amplitude, because it's moving to the right. It's not the equilibrium position. Someone said you want to make it so that 0.6 cosine of 4t plus phi. I can understand that, but that's basically also what Ange is saying, that this is the amplitude. That doesn't work, unfortunately. What do these represent? How could I write them somewhere down here as a piece of information? So the closest answer so far has been what Andrew said. Initial position. That's the closest answer to what I... This is the initial position, right? Set it equal to x of t. Okay, that's also on the right track. Okay, so what would the value of t be in that equation, Joanne? 0, right? So what if we wrote it like this? X at time equal to 0 equals 6 millimeters. Does that seem accurate? Okay. And then what about the velocity? We do the same thing, but that's the velocity at time equal to 0 is 3.2 centimeters per second. And we can change the units as we need to here, of course. But okay, so now we've got all of our information. We know it starts at t equal to 0, and we now have a later time that we're going to use, right? So what we want to do is to find this equation. We want to figure out what that equation is, which means we need to find a, and we need to find phi, and we're probably also going to have to find the angular speed. Okay? Anyone have any ideas about how we could go about doing it? There's more than one way to do this. There's at least 3 different ways you could do this that are all quite different, but get you the same answer. How would you all like to approach this? Use the energy equation. Okay, let's see if we can do that. Use this one. Okay, let's pop that one down here and see if it's going to be useful to us. Seems reasonable to me. Okay, the energy equation has A, which we do not know. It has X, which we have one value for X, right? and it has v, and we have one value for v. So we kind of have 2 out of the 4 variables here. So at least on the surface, we can't use this immediately, but that doesn't mean we won't use it later. We can probably use it later if we figured out what omega was, or we figured out what a was. Either way. Oh, is omega given? It is. Oh, great. My bad. I wasn't. Yep, omega is given. Okay, so we can straight up use this. I was confused for a second because I was like, that seems like it should work. I thought that would work. Okay. There'd be no way to find omega if it wasn't given, by the way. It would be impossible. It's not possible. You need to know what this value is. Okay. So we know omega. Yeah, we're good. We can find a, right? Yeah, okay. So let's do that. This equation, let's rewrite it. It says basically omega squared times a squared minus x squared is equal to v squared. So we want to solve this for a. So we're going to have a squared is equal to v squared over omega squared plus x squared. So, and again, these v's and x's here represent any v or any x as long as they occur at the same moment in time, which both of these do, right? So this means that a is going to be equal to plus or minus the square root of v squared. Now, it's probably a good idea that we just convert everything into the same unit. I'm going to use centimeters, I think, instead of meters. I don't want really big numbers. So this will 6 millimeters, not. Maybe it makes more sense to use millimeters. 6 millimeters would be 0.6 centimeters, right? Okay. So V is 3.2 cm per second. Divided by omega, which is 4 radians per second. Both of these are squared. Plus x is 0.6 centimeters. And we just need to square that. A is actually always going to be positive, but I put plus or minus here just, because might as well. Okay, what do we get when we calculate this? You get 1? Yeah, that sounds right to me. 1 centimeter. 3.2 divided by 4. Yeah, squared plus, it's going to be 1. Okay, so we get as an answer 1 centimeter. That's nice. Okay. Now, we only have one variable left now, right? Our goal is to write x as a function of time so that we can find where the particle will be 0.4 seconds later. And we've already found a, we have omega. It's just phi that remains, right? Phi is the last thing that we need to figure out. So in order to figure out what phi is, we're now going to need to use these two pieces of information as I wrote them. That is to say x of 0 and v of 0. I think we need to use both, but I could be wrong. So let's try this out. We know what x of 0 is, and we have a full equation that will have every variable except for phi. So let's write them out. So what we can do is we can say x of 0 is equal to a, which is 1 centimeter, multiplied by the cosine of omega t, omega's 4. I'm just going to write 4t if that's okay with everyone, plus phi. But t is 0, so it's 4 times 0. And this should be equal to x at that point, which is 0.6 cm. So putting that together, we have 1 centimeter cosine of phi is equal to 0.6 cm, which means cosine phi is equal to 0.6, which means that phi is going to be the arc cosine of 0.6. So phi is equal to. Now the thing about doing this is you got to be a little bit careful because arc cosine, when you plug it in your calculator, is only going to give you one answer, right? But there could be multiple solutions, right? So I get 0.927 for this. Do you all agree? And in degrees, I think that's like 37 degrees, basically. if you happen to do it in degrees, you would get 37 degrees. But we do want it to be in radians because all this stuff is going to be in radians. So the next thing to do, yeah. Is it plus 2 pi? No, I think it's 180 minus this number or something like that, but here. So, okay, this is something where I always have to check just to make sure. So the cos inverse of 0.6 is 0.927. That means that cosine of 0.927 gives you 0.6, right? If I do the cosine of, I think it's pi minus that, you should get the same answer. It's either pi minus or pi plus. It's not that. It's probably pi plus. Cosine of... Alright, I'm not going to worry too much about it right now. We'll figure it out over the break. Plus pi? It can't be right. It's not going to be plus pi. It would just be 2 pi, right? I'm thinking of the arctan. Okay, just forget what I'm saying. For now, I can't remember how it works. Okay, so arc cosine gives you this. So let's just check. Our other piece of information was that v of 0... So this is possible that this is the answer for pi. Oh! It's plus or minus with cosine. That's what it is, right? Because if you do the cosine of negative 0.927, don't you get the same answer? Yeah, that's what it does. This is plus or minus, basically. The arc cosine is always going to... It's just like the square root. You always get plus or minus on here. Okay, v of 0. Let's check this, because it could be either. So v of 0 would be... So now we need the velocity equation. So x of t was a cos of omega t plus phi, which means v of t is going to be negative a omega sine of omega t plus phi. So v of 0 is going to be negative a omega sine of phi. And we know what this is. So v of 0 was 3.2 centimeters per second. This is equal to negative a, which we calculated to be 1 cm, times omega, which was 4. Sine phi. So this means that 3.2 divided by 4 negative is equal to the sine of phi, which is equal to negative 0.8, which means that phi should be equal to the arc sine of negative 0.8. And that, okay, did I do everything right? I'm going kind of fast here because I do want to give you all another break before we go on to pendulums. Does anyone see a mistake I made yet? Please let me know if you see something. So I think we're going to get negative 0.927 out of this, right? So this is the part about this that's like a little bit tricky, is we found an answer for the amplitude, right? No problem. We got the amplitude. It's the phase angle that's going to be kind of tricky because that's going to almost always involve inverse cosines and stuff. There's other ways to do this. If you find a better way to do it, you can do it that way. But you got to be careful because here, if you just put arc cosine at 0.6, you're going to get positive 0.927. You just need to remember there's two different solutions because the actual answer in this case, I believe, is this one right here. Right? Yeah, the phase angle in this case should have a negative sign, right? So what's our functions, right? Now we can actually... Derivative of this, negative sign here. There was a negative sign here. That became negative. Nothing else was negative because it was going to the right, right? The velocity, just to make sure. Initially, the particle is 6 to the right, moving to the right. Yeah. Yeah. So, how do you know if it should be positive or negative? The way you know, Joanne, is you have to do both the x of 0 and the v of 0. The initial x position and the initial velocity is going to tell you the answer because basically it's going to give you... you understand? Okay. So, we'll come back to that in just a second. Let me write the answer down. So x of t now, we know, is equal to 4... No, no. A is the amplitude. That's 1 cm, right? And we multiply that times the cosine of omega, which is 4t, plus phi, but we're not going to put positive because phi is a negative number now. So it's going to be 4t minus 0.927 radians. Okay? And our goal here was to figure out, let's go back to what we were trying to do, where will the particle be 0.4 seconds later? So to finish this problem, we have to plug in x of 0.4 seconds is equal to 1 cm cosine of 4 times 0.4 minus 0.927. And now we need to plug all of this into our calculator. So again, still needs to be in radians. So we do cosine of 4 times 0.4 plus or minus 0.927. And what I get is 0.782. And since the answer is positive, that means it's going to be 0.78 meters to the right. Now let's ask a couple questions to see if this is reasonable. The angular speed was 4 radians per second, right? What's the period? Well, the period is given by 2 pi divided by omega. So in this case, that would be 1.57 seconds. Right? 1.57 seconds is the period, right? We were trying to figure out where it was going to be 0.4 seconds later, right? So it started here at a position that was at a position that was 6 millimeters, or 0.6 cm. The total amplitude is 1 cm. And 0.4 seconds later, it looks like it's at 0.78 centimeters. So it's basically, so the amplitude is somewhere over here. This is x equal to a. And at 0.4 seconds, that means it's somewhere right here. Can anyone tell me before I do a calculation, is it moving to the left or the right at that point? What do you think? Is it going left or the right, or to the right at that point? What do you guess? Take a guess. Just take a guess. We found out that at 0.4 seconds, it's at a position of about 0.8 centimeters, right? So if this is the amplitude x equal to a, and it started at about 6, it's now at about 8 centimeters, somewhere in between, right? Do you think it's going left or right? Take a guess. Just take a guess. If you don't know, just take a guess. But if you can use your brain to figure it out based on some of the stuff we've done here, that's even better. Make a prediction. What do you think? Is it going left or right? Assuming left. It seems reasonable that it should be left, right? Because it seems like it probably, in 0.4 seconds, it probably started here and then got to here and then now is turning around and going back the other direction at this point, right? It's probably what's going on, right? And the way that I know that is if I take t over 4 is actually equal to about 0.4 seconds, as it turns out. So this is basically a quarter of the period. This number, 0.4, a quarter of the period. So it can't have only gone from here to here. It must have gone from here all the way back around to here, kind of. That's what I'm thinking. But you can plug in values here and you can figure it out, right? Okay, one other question before we take a break. What would have changed in our problem? What would have changed if instead of it saying that it was moving to the right with the speed of this initially, it was moving to the left initially. What would have changed if I told you that it was moving to the left initially in our final equation here? Does that make sense? If we changed only one thing and we made it so that instead of making this velocity vector start off to the right, it was starting off to the left. The phase angle. That's exactly right. That's exactly right. And the answer would have been the same. The phase angle would have still been 0.927, the value of it. But the difference is that this would have given us a positive answer, right? And so our correct answer would have been the positive solution, not the negative solution. Anyway, that took a little longer than I thought it would, but it's totally fine. I mean, this problem is well worth talking about. You're going to see a decent number of problems like this on your homework, and, you know, want to make sure that we, yeah. So we're going to take a shorter break here just because we have very limited time. We'll just take a 5-minute break. God, I hate only taking 5 minutes. I'm not going to do that. I'm not going to do that to you all. We're taking a 10-minute break. We'll take a 9-minute break. That's what we'll do. For whatever that is, I'll type in the chat.